What's up, scholars? I'd like to run you through quickly a little bit of a tutorial on how to use graphical analysis to do especially part 3 of our lab here. Parts 1 and 2 you can do by just answering the questions, but if you go over to the side here, it'll take you straight down to part 3, friction. What you're going to do before we start is make sure you've downloaded Vernier's graphical analysis. The link to that is on our Google Classroom page. So let's just follow this instruction step by step. Click on the friction and check all the boxes. So let's do that. I'll pull my window down here. So resize that. So friction, let's just check on all the boxes. Okay. So next it says, start pushing the box, increasing the force slowly. There's a force that's opposite that you're applying. What's the name of that force? I'll let you answer numbers 3 and 4. Okay. Now, after you do 3 and 4, you'll have to reset it. So you can, at any time, you can click this button to reset, and we'll just re-click these boxes here. So let's jump down to number 5. This is really where you're going to collect data and actually put it into the graphical analysis software. So what we're going to do is we're going to push the box and find the force that's required to make the box actually begin moving. Okay. And so let me show you what that's going to look like, and then we'll go in and actually collect the data. So I just have a regular box here. I'm going to apply 50 newtons of force. You can see here a bunch of information. So I have an applied force to the right in orange, and of course equal and opposite force, Newton's third law. Here it happens to be friction from the surface of the box and the ground pushing to the left. Okay. Once we do that, right now you'll notice that the sum of the forces is 0. They're completely balanced, and the speed has remained 0. Nothing's moving. This is static friction. So if I add more force, now I'm up to 100 newtons, doesn't move. If I do that one more time, hey, it starts to move. So my speed goes up. You'll notice the speed is increasing. The rate of change of speed is increasing, so it is accelerating. And, pardon me, the sum of the forces is 56 newtons. So that's how much extra force I'm applying versus what the ground can actually supply. Right now, because I'm sliding, this is what we might call dynamic or kinetic friction. Okay, so I'm going to pause that and reset. Let's see what we actually need to accomplish in here, and we'll collect a data point or two together. So it says, repeat the procedure such that you complete the table below. So you're going to do what's in the picture there. And there are a few hints here. So we're going to fill in this data table. Weight, as we did in class, is just mass times the acceleration due to gravity, or mg. The magnitude of the normal force is just the magnitude of the weight, so just mg. So these two columns are going to be the same. And then finally, the maximum force of static friction is that force that I applied right before it starts to move. Okay? So what we'll do, we'll fill this one in, and 50 times 9.8, I happen to know, is 490 newtons. Remember, we just did mass times the acceleration due to gravity. We get 490. Now, of course, if we look at our picture here, the amount of weight force being applied downward by the box is exactly equal to the normal force of the ground pushing up on it. So we just fill in that this one is also 490 newtons. And then this is the part that we actually have to manipulate PhET to get the maximum force of static friction. Once we actually get that number, I'll show you how to put that into graphical analysis. Okay. So you have to be a little bit careful here. And of course you can just reset if it's not working. So I'm going to show you what that might look like. So let's say you get a little overzealous. You push it 50, it's not moving. You push it 100, it's not moving. Okay. And we've gone too far, it's moving. What you'll notice is we can't go back. So it moved somewhere between 100 and 150. If we step this down to 100, it's still moving forward because we're dealing with kinetic friction. Which is to say, if you make it move and is going too quickly, just hit reset. So I'll turn all these back on. And let's try that again. So let's get to 100, and then let's step this up gradually. I happen to know where it is. So I'm at 125 newtons for 50 kilogram box, 490 newtons of weight force. And I go one more, and it begins to move. So the maximum amount of force that it can apply, the frictional force, was right at 125 newtons. As soon as I went above that to 126, everything started moving. Now I'm in the realm of dynamic or kinetic friction, where it's actually sliding. So I can show you that. Now that it's sliding, but we can't do any static information with it. So let's put that information over into graphical analysis. So let's go over there. When you open graphical analysis, it looks like this. We're going to go to manual entry. That just means we're going to type the data in ourselves. We're going to go over here. The first thing that we want is our column option is going to be the mass. Oops, I'll do all caps there. So the mass is measured in kilograms, and the mass that we're going to use is 50 kilograms. The next thing we want in there is, let's say, the normal force. Okay. So let's check our thing here. Yep. So normal force measured in newtons. This is how I want you to set it up. You can see in the document there. So let's go back over. So normal force, I need to add that is in newtons. Excellent. And then, so we determined that was 490. Those were just calculating by hand. And then what we can do is we can add one more column by clicking this little knob here and say add a manual column. That needs to be the maximum static friction force, and that's also measured in units of newtons. So what we're going to do is we're going to have normal force on the y-axis, as you can see. Maybe you can see. Oops, no, we're going to have the friction force here and the normal force over there. So this is going to be the max static friction, and this is going to be the normal force. Okay, and so I need to plug in here, pardon me, that it started to move after we exceeded 125. So 125 was the maximum force that it could handle. Okay, and when I do that, it plots a point. Yeah, it plots a point for me. Now it's scaled kind of funny. Let me show you how to rescale this so that it looks sensible. And then we'll collect one more data point together. Then I'll show you what this looks like when it's finished, so you have some sense of what to do with it. So go to Edit Graph Options. What you can do is you can say I want to always see 0 in the x-axis. And I want to always see 0 in the y-axis. So it put my dot way up here to the right. Let's name this. Let's name it static friction versus normal force. Okay, and that should show up at the top here. Okay, so let's do one more. Let's go back together. So we filled in our table. We got our first data point. Let's get another data point. So go back to the table. We need to put in 90 newtons, which I happen to know is 992 newtons. Pardon me. So 90 kilograms is 992 newtons. When you take mass times acceleration due to gravity, that's the same as the normal force. And what we'll find is, I forgot to it's 125. And so what we'll find is we need to put on 90 kilograms worth of force, and we need to see at what force level does it actually start to move. So let's reset this. And let me increase it here. So we have an advantage. We actually already know that we can go straight up to 125. Oop, I went a little farther, but that's okay. It's not moving. I'm going to risk it and go one more, and then we'll gradually go up. Let's see what we get. Okay. So far we have no real way to predict how much it's going to be. Not really. So 225. Okay, it just started to move after 225. Okay, so we're going to put that into both here, so 225, and we'll type this into here. So 90 kilograms, 992 was our normal force, and then static friction, we got it to 225. So when I hit enter, you should see another data point show up on our graph. Boom. So now we have 2 data points, and what I'm going to do now is I'm going to pause the video and open up the completed version of this where I've got it all in there. All right, so let's assume we've filled this in. You can see in my graph I actually filled in all the rest. So for 120, 150, and 180, all I did there was stack more people and stuff on there to get to the appropriate mass. And then what I did was I ended up doing a slope, finding the slope by doing a curve fit. So let me show you that. That's how we're going to answer the slope. So I had it turned on there, but let me just show you. So you go to Apply Curve Fit. This is just like vernier video analysis. So you'll click Apply Curve Fits, and it will do it there. And we get the slope. So we'll type that in to right here. And then from there, I'd like you to try to answer what does that slope represent. So use your best reasoning skills to give whatever answer you think is best for what does the slope represent. And then you're going to do the same thing for kinetic friction. This is where things are going to be a little bit different. So I want to also walk you through the kinetic friction section. Okay, so in terms of kinetic friction, we actually have the same table here. So I've scrolled down just a little bit. We're doing essentially the same procedure with one minor tweak to it that actually I'm hoping is going to help you understand what's going on, the difference between static and kinetic. So check this out. So we're going to put 50 on. We're going to do the same procedure. So this was 490, 490. Now, we can make a prediction here. We know that the force of static friction, the most that the box could provide, was 125 newtons. We've also discussed how actually once you get it moving, it's easier to keep it moving. So we can anticipate that the force of kinetic friction is going to be less than 125. So let me show you what I mean. So we are going to check on all of these boxes. Let's get this going. We know that at exactly 125 newtons, it'll start to move. And then watch what happens. I want you to pay careful attention to the friction force applied. Right now it is static. As soon as it begins to move, you're going to see this arrow get shorter because the box cannot supply as much kinetic as it can static friction. So check this out. Watch this red arrow. Boom. It got shorter. And it got shorter by 32 newtons. It's this only went up to 126. But what we can do to be sure is we can back this down. Oops, wrong way. We can back this down. Oops, we need to get it moving again. Okay, it's moving again. We can back this down until they're equal to one another. Okay? So take a look at this. We're still moving at 4 meters per second. We're still applying a force. There's still a frictional force. So this box has inertia. We're applying just enough force to get it moving. There's a particularly challenging exercise that I've done in the past. We have to push a heavy sled across the ground. This is the same situation. Okay, football players and other athletes will do this kind of thing where you're pushing it across the ground. What we're exploiting here is the frictional force. Once we get it moving, it applies a strong force against us, but we can still move it at a constant speed. Okay, so we're in equilibrium here. We've got the same amount of force forward as backwards, but the net force on it, the sum of the forces, is exactly 0. So what do we do with this information? Well, the applied force here, the friction force, is exactly 94 newtons. So we'll punch that in there. And then all you do is fill this in for the remaining ones. You should end up with a graph that looks sort of like this. And I'm just going to give you a little bit of a spoiler, a little bit of a hint. Because we know that the static friction is stronger than the kinetic friction, we can actually sort of anticipate, this should open here in just a moment, we can anticipate that the slope of the static friction graph is going to be bigger than the slope of the kinetic friction graph. Let's see what that looks like. Okay, so here's what we've got. I'll turn on the graph legend so y'all can see. Boom. So in red we've got static friction. That's up here. In blue, we've got kinetic friction. That's down here. We can look at their slopes and compare them. So in some way, this slope represents the amount of stickiness that type of friction has. It is harder. It requires more force to overcome the static friction than it does the kinetic friction in here. So basically, you should have a graph that looks just like this one when you're finished, and then you'll just answer the remaining questions that are in there. Please do reach out to your teacher with any questions that you might have over this. I'm hoping that this video was helpful. Of course, attend office hours this week if you're having any difficulties whatsoever. Thanks so much, scholars.